Hi all, now let's continue with variational inference. Before going to the details of what variational inference is and how it relates to our neural networks, let's revisit briefly the concept of marginal likelihood because we're going to need it. So assume as an example that we have a population for which we have a few statistics, for instance the color of the eyes denoted with X and the nationality of a person denoted with Z. Now, having statistics means basically having a table which stores all possible combinations of eye colors and nationalities, and for each combination it provides us with a probability. So since this is a probability density function in the end of X comma Z, then all these probabilities have to sum up to 1. If we want to know something about the distribution of the colors of the eyes in this population, regardless of the nationality, then we have to resort to the so-called marginalization operation. Specifically, we have to sum up over all possible outcomes for each of the eye color instantiations, and that way we are making sure that all possibilities are taken into account. So for instance, to compute what is the probability of having brown eyes, we're going to sum up the probabilities of having brown eyes while being Dutch, while being Greek, while being Chinese, and so forth, until we visit all possible nationalities. And we do the same for other eye colors. Since the marginal likelihood is still a probability density function, it means that it has to sum up to 1. And indeed, when we sum up all our entries here, we obtain 1. Now, marginal likelihood is of course possible when we have latent variables. It doesn't work only with visible variables. Assume, for instance, we have this set of pictures, and the bottom half of our pictures is visible, while the upper half of the pictures is blacked out. Now assume also that we have a good model, P of X comma Z, basically capturing the correlations between the visible and the latent pixels. And we want to now compute how likely it is to have such a half picture, so basically these bottom halves. To do that, we again have to marginalize out over all possible latent pixels. So basically this means we have to take into account all the possible upper half pictures that could take place, sum up their respective probabilities, their respective joint likelihoods jointly with the visible pixels, that is. And by doing the summation, then we can basically get an idea of how likely it is to obtain each of these bottom half of the pictures. To get a more intuitive understanding, basically this means that, let's focus on this picture. So in this picture we see two legs. Probably there's another elephant here. Maybe there's another here, and maybe there's another here. So that is one possibility of how our latent pixels might be looking like. However, that's not the only possibility. It could be that this elephant doesn't exist, or this elephant doesn't exist, or this elephant doesn't exist. Each of these cases could produce the same bottom half. By summing over all possibilities, we compute in the end how likely it is to have this bottom half under all possible latent upper half images. In our case, we are interested in latent variable models, as we discussed in the previous sub-lectures. Basically, we want to couple our visible variables X, which correspond to the data, to our observations. So we want to couple them with latent variables Z, and these latent variables Z ideally and hopefully capture higher level features which represent what is in X, so capture the real content of X, removing possibly the various nuisances. And in a way, you could also say that if we would have these latent features z, we could reconstruct or generate back our image x. So with latent variables, we can explain our observations. And again, since what we have is only the observed data, the observed variables x, and we want to perhaps capture of how likely it is to have these observations, we have to marginalize out over the space of all possible latent variables. In case z is a continuous variable, then we have to perform an integration. And if it's discrete, we have to do summation as in the previous slides. Now, since this is a joint likelihood, it means that we can decompose it, right? And obtain a likelihood term of x given z times the prior over the latent variable c. And this expression can be further reformulated in terms of an expectation here. So in an expectation, we have two important quantities. One is the quantity that we want to, whose expectation we want to compute. So basically here, we can say that our the probability of our observation given a latent code, a latent variable, is what we want to average over. And a second important quantity is the probability density function, according to which we're going to basically take the expectation. So basically, the density of the probability space such that we can compute the average over. So for instance, if our space has a Gaussian measure, we're going to sample more points from the middle rather than from the edges. Whereas if it would be uniform, we would sample from everywhere the same. A latent variable model can also be viewed as a generation model, so a generation process. First, we generate a new sample, in our expectation from the prior. And then, given this sample, we can generate a new observation point, x. Unfortunately, the joint likelihood is not always tractable, or, well, anyways, it can be hard to compute. So, in the end, we are interested in finding good parameters for our latent variable models, and these parameters might be expressed by theta. The reasonable thing to do is to try to maximize the log likelihood, and by inserting the marginal likelihood in our log likelihood, we obtain this sum log sum expression. Now, we have seen some similar formulation in the Boltzmann machines, and we saw that actually summing over all possible z's is actually a nasty computation. Just for three-dimensional z vectors, we have to iterate over all possibilities, and if we increase from 3 to 20 dimensions, so not a huge increase, this means that we would have to visit over 1 million different combinations. That is for each image x. That stands for a huge amount of computation that is not tractable. It's not easy to to handle, and things become even more complicated when we have continuous variable z, because in that case we cannot enumerate over all possible instantiations of z. In that case, we have to take integration, and integrals make things even more complicated usually. So how do we make things tractable? In the previous lecture with the Boltzmann machines, we saw a few ways to address intractability. In this case, one way is to resort to naive Monte Carlo. So for each data point x, again we take the log sum. Now we ignore for now for simplicity of notation, we ignore the external sum over all data points. So now we have the log of the sum over all latents. Now we can actually see this as a very big summation, right? So that's like a summation of P1 plus P2 plus P of like absolute Z, where absolute Z stands for the total number of combinations of Z. We could approximate this summation. This summation is the quantity we want to compute. We can approximate this summation by you know, taking an average, right? So if we were to take an average P like that, and then we would multiply it with the number of components here, so the summands, we would basically be able to reformulate our summation. So the idea with the naive Monte Carlo is that instead of computing the average of you know, P bar here, using all a very high number of combinations of Z, we can sample a few, let's say 1, 2, 3, 4, 10, compute the average, and then estimate the final sum, of course taking into account that currently we use only a smaller set of items to compute the average. So this is exactly what I described here in this mathematical formulation. We have the Z here corresponding to the number of summands and the average, so the expected value. The sampling, how do we do the sampling? We can do it uniformly, right? So if we have, like, let's say 1,000,000 possible combinations, we randomly pick 10, and this is it. We compute the average, and afterward we adjust by dividing by big K, so the number of random samples we took, and like that we can approximate our total summation. This process is very intuitive, straightforward to understand. However, we got a problem here. The problem is that it doesn't scale, because in order to compute good estimations for our expected value, so for our sample average, we need a very large number of these guys here. So maybe 10 is not enough, maybe you need 100 or maybe even more. You can think of this intuitively as follows. Out of all these items in the summation, a few will have large values, others will have smaller values. By taking random elements in the summation, we're more likely than not going to have smaller components used for computing our average, which means that our average will be not very accurately estimated, and therefore the total sum that we estimate will be still not very close to the real sum. So in a way we could say that by randomly sampling from our space Z would lead us in sampling from low density regions, so from regions where we've got small probabilities, therefore unimportant joint likelihood terms, which do not help us recovering accurate estimates. In a more technical jargon, we would say that this is a high variance estimator, in the sense that if I repeat the process, so if I pick like 10 summands now, I compute the average and calculate the final sum, I would get one number. If I were to repeat again the same process with the same number of random quantities, random samples I'm sampling, I would get another estimate, and the two estimates would not be very close to each other. There will be a high variance in these statistics. A better way to address this problem is to use importance sampling. So if again I have my summands in a very big sum, it would be better if I were able to focus on a few of those that is actually, you know, they're large enough, therefore they're important enough for the final summation. These would reflect better our final average. So how we can do that? Well, if theoretically we had a nice distribution over the space here of basically over Z's, we would be able to sample with higher likelihood z's around the important parts of the space. This doesn't mean that we ignore the rest, but we sample more from the important bits, and of course we have to normalize to account for the fact that we're sampling only from a specific part of our space Z. How do we do that? Well, again, in the log sum term we had before, we have two now densities. So we multiply and divide by the same density, q parameterized by phi. Right, since we did multiplication and division by the same quantity, there is absolutely no problem. And now we can rewrite this as an expectation again. Mind you here the dual use of our q phi. The red one basically is used to, as our probability density function from which we're going to sample our expectation. So it is used as a sampling mechanism. If we were to pick, for instance, a Gaussian distribution here, we would, represent here sampling Gaussian sampling. The green q phi, on the other hand, acts as a normal function, which you give an input z, and you obtain a value, whatever value. So again, if we had a Gaussian here, I can input any input and then see what exactly is the output of my probability density function, and that is exactly the purpose of the green q phi. It acts as a function which normalizes the joint probability that I'm computing for x, z. Right. To bring some more intuition, if my q phi returns large values, it means that I'm going to sample from it more often, right? So in my Gaussian example, these are, this region where I'm going to obtain the most of our z's. So if I were to sample, most of my z's would be around here. So these would be more often than not computed in our estimation of the sum. However, at the same time, for the same z, I would divide by the same large value the joint likelihood. So that way, I counterweight, I counterbalance the added effect that I have obtained by sampling more from these, more important regions. Now, important sampling to Monte Carlo scales much better and with much lower variance, because we are more likely to use very similar summands in our estimation for our averages. However, the problem is, how do we obtain such distribution q phi? What we can do is learn it from data. So together with, as with everything else, we can learn also our sampling distribution q phi from our data. So then our learning objective is again to maximize the log probability, and this can be done by optimizing both parameters theta and phi. Now, the logarithm of the expectation, the expectation is an integral, so the logarithm of an integral is actually in most cases unknown. It's not very convenient for derivations computations. It leads to intractability because we cannot easily come up with function forms that are comfortable for us computationally. It would be much nicer if we could swap the logarithm with the expectation, such that we, instead of the logarithm of expectation, we have the expectation of the logarithm. And that would be very nice, because, for instance, if our joint likelihood would belong to the exponential family, the logarithm and the exponential would cancel each other out and have much nicer, much faster and perhaps efficient computations. Now, let's see if that is possible. Well, it's not really obviously possible right away. We cannot just make them equal. However, we can use Jensen's inequality. And according to Jensen's inequality, we have a concave function h, and the concave function h receives as input a sum. The output of such an input would always be larger than the sum of individual applications of the inputs on the same function h. So basically this means that if my function is concave, like the logarithm here, if I take any 2 points on the line and I connect them with a line, the line will always be below my curve. Now this is very convenient because it tells us that basically we can sort of replace our original maximum likelihood objective by a lower bound, right, which has exactly the form that we desire, so an expectation of whatever function follows. How does this work for us? By applying Jensen's inequality on our learning objective, therefore, we obtain a lower bound counterpart, which is the expectation of the logarithm of the important sampling quantity, so the logarithm of my joint likelihood over the density function that I'm learning, the important sampling density function that I'm learning. And this expectation is computed with respect to my important sampling density function. Now what we did is we replaced the original machine learning maximum likelihood objective with a quantity that is always smaller, that is guaranteed to be smaller. So this means that since this is always smaller, by optimizing it, by making it as large as possible, then the left quantity here, which is above my lower bound, will be by definition also optimized. So by improving our term on the right, we're guaranteed to improve our term to the left, and that is because we have a lower bound. Now this term here is a tractable and comfortable quantity, so a much easier optimization for us. It is an expectation like before, so we take the expectation over a logarithm, and since this is expectation, it means that we can easily apply Monte Carlo sampling, and since we've got the logarithm, we can couple it well with our for instance exponential functions, and then remove nasty nonlinearities that might make things more complicated than they should. Basically, this is something. This is what variational inference does. This is variational inference, where we're trying to replace a quantity that we cannot easily compute with a distribution that is much easier to compute, and trying to optimizing the parameters in a way that our approximation is as close as possible to the true one. So we can actually repeat the same formulation from a different point of view. We can say that in our computations, the posterior is actually the most problematic one, because the posterior, the true posterior, is computed as the joint likelihood over the prior over my observed data x, and the prior over so the marginal, this is a marginal likelihood, so this prior, this is like total probability is the marginal likelihood of x after we integrate over all possible z's, and this integral is a nasty one, we cannot compute it easily. So variational inference tries to approximate the true posterior p of z given x with another distribution. So this is one distribution, we try to approximate with another distribution such that we make it, we make the approximation as good as possible. So let's say my probability density function is like that, then with variational inference I'm using a simpler distribution usually, so q phi represent simpler family distributions like Gaussians, and then I'm trying to find the Gaussian that fits the best way possible my true posterior. By minimizing therefore the difference between my approximate posterior and my true posterior, we can obtain again a formulation which is the elbow from before, so the expectation over the logarithmic quantity plus my logarithm, so my log marginal likelihood. So this quantity we said is known as the evidence lower bound, or elbow, and it is directly connected with the log marginal likelihood as well as the KL divergence between my approximate posterior and my true posterior. This is called evidence because the KL term here is a quantity that is always positive, which means that if we drop it, then we have that my log marginal will always be larger my evidence lower bound, right? And the log marginal also called evidence. This formulation is actually interesting because it implies that if I have a higher elbow, then I'm going to have a smaller difference to the true posterior. Sorry, should not be here. And the reason is that the log p of x does not depend on the model parameters, right? So it doesn't depend on the model parameters. It means that it won't change. And the higher this becomes, the closer we get to the log marginal. Therefore, we have better latent representations. Also, higher elbows means that the gap to the log likelihood tightens, so we have better density models here. Graphically, the variational inference model can be simply depicted as, this is my family of all possible functions. So let's say again, I want to approximate this true posterior, right? And this true posterior here corresponds to this dot with some sort of Gaussian. I don't know which Gaussian, but it can be like this one, or it can be that one, or it can be that one, right? All these possible Gaussians are within this model space, and variational inference tries to find the Gaussian that looks the closest to my true posterior. Examining the elbow allows us to make several interesting observations. First, we can see that elbow is in a way balancing between the reconstruction and the prior. So by decomposing this term here, we can arrive in a formulation such that on the left we have our reconstruction. So given my latent variables, I'm trying to reconstruct my input x and take the expectation over. So we're marginalizing over all possible latents. This means that I'm not sure exactly which latent reconstructs my input, but if I take an expectation over all possibilities and average, then I'm going to get a good reconstruction. The second term is the KL term, which basically minimizes the distance between my approximate posterior, my density function, the density function that I'm learning, with a true prior P of z. So the first term encourages the reconstructions that maximize the likelihood, so make sure that returns good reconstructions, while the second term minimizes the distance of the variational distribution from the prior. Another way we can rewrite the elbow is by expanding such that we obtain an expectation over the log density and an entropy term. Under this formulation, we can understand the elbow as an objective which aims to maximize the joint likelihood, so something like the Boltzmann energy, like generation, so the true generation in our model, while maintaining enough entropy in my learned density function. we want that because otherwise we might obtain pathological point estimates for z. So we want to make sure that my function, my important sampling function that I'm learning for z, is not going to focus only on a few points where I'm going to get high values. We rather get a distribution over all z's. Variational inference generally underestimates variance, and the reason is the way we derive the elbow. So in one of the two ways we derived the elbow earlier, we saw that we want to minimize the distance from the distance of my the important sampling function that I'm learning as a density function from the true posterior. And by doing so, we see that we have here this ratio, right? Now, what the model does is, it tries to approximate, in reality, the true posterior here. Like, that's our intention, that's what we want to do in the first place. However, the model, especially in the beginning, cannot really know exactly the form of P of z given x. More importantly, it cannot really know which areas are going to have very low values for my my true posterior. Now, what does this mean is that imagine that this has a very small value, let's say 0.00001, and then my model decides to assign a large value like 10. This ratio and the logarithm thereof will obtain a very large value because we divide a very large number with a very small number, and that can create a huge divergence between the two quantities that I want to minimize, in fact. So what the model implicitly does, it prefers to pick a single node for which it knows that there is enough density around for the P of z given x, so that the denominator is always large enough, and any mistake it will do will not cost the elbow to skyrocket the ratio. This is why variance is underestimated. So you pick a mode and you focus around that, and it doesn't matter if there's another mode with higher density, with high enough density to be captured. The model prefers to stay on the safe side and focus on what area of z space is familiar to it. How can we overestimate variance? Well, you could use the forward KL. However, and in that case we would have the reverse effect, right? Because in that way the model would prefer putting some quantity for the Q phi everywhere. In that case, if my true density is somewhere large and the model makes a mistake, again the ratio will not skyrocket. What is more, the forward KL is not always as easy to compute. So in any case, the reverse KL is the way to go. Thank you.